So this is MAT221, Calculus 1. We're in section 3.7 talking about derivatives of logs and logarithmic differentiation. This is video 2. We were talking about finding the derivative of x to the cosine of x. So let's go through this procedure to show you how we would take the derivative of this function when we have a function raised to a function. First thing we would do is take the natural log of both sides of the equation using our law and then use our laws for logarithms. All right, so let's take the log of both sides, natural log of both sides. Now remember, our natural log rules say that if I take the natural log of a function that has an exponent, the exponent can come to the front of the log. Remember, that's one of our many rules that we have for logarithmic properties. So this can be rewritten as the natural log of y equals the cosine of x times the natural log of x. All right, so now I took the natural log of both sides and then I manipulated and simplified by using one of my rules for logs. Next, take the derivative of each piece of this expression with respect to x. Now here, if you notice, we're going to have to take implicit differentiation because remember the y and x don't match. So if I take the derivative of the natural log of y, that's going to equal 1 over y multiplied by the derivative of the inside function, which is dy dx, implicitly. The derivative on this side, we would have to incorporate the product rule, which would be the first times the derivative of the second plus the second times the derivative of the first. Doing this, we get the expression 1 over y dy dx equals cosine of x times 1 over x plus natural log of x multiplied by the sine of x. Excuse me. Remember, when we do implicit differentiation, it's the derivative of the outside function here, which is 1 over the function, multiplied by the derivative of the inside function, which we don't know what it is, so we say dy dx. Next, we solve for y prime, or we solve for dy dx here. So I would multiply both sides by y. Now we could leave this like this, as we do most times when we have implicit differentiation. Or we could also incorporate this. We know that y is equal to x to the cosine of x. So we could substitute this original function back in for y to get an expression of dy dx in terms of just x. There is our first logarithmic differentiation. So I wanted to look at a couple more examples that I didn't have on this original PowerPoint. So let's look at your worksheet in the worksheet folder on logarithmic differentiation. It's in your Blackboard folder under the worksheet folder. And I'm going to look at this, this method a little bit further. So there's more examples here for you to look at. So at the very top of this worksheet, it says, remember, the method of logarithmic differentiation can make finding derivatives enormously easier. Use this method to differentiate functions that are products or quotients of multiple factors, and when there is an exponential function raised to a functional exponent. And again, here's our steps. We would take the natural log of both sides, simplify using our natural log rules, differentiate with respect to x, and then solve for dy dx as a function of x. So in the worksheet, the first example looks something like this. Now, quite honestly, we could use the quotient rule and then again incorporated with the chain rule, incorporated with the product rule. There would be a lot of rules here. We can still do this actual derivative that way, but it gets pretty complicated. So sometimes logarithmic differentiation will simplify the process a little bit for us. So I'm going to show you how to do this particular function when you notice it's the product or quotients of multiple factors here. I'm going to show you doing the derivative using this process of logarithmic differentiation. So the first thing that I would do is take the natural log of both sides. Now, when I take the natural log of the left side, it's simply the natural log of y. But when I take the natural log of this side, we're going to use all of our different properties from pre-calculus for the natural log of a quotient and a product, and then also using this idea of exponents also. So when I take the natural log of this side, I get the natural log of x minus 1 plus, because this is a product, and remember the natural log of a product is equal to the sum of the natural logs. Remember, when I take the natural log and I have an exponent, the exponent drops to the front of the natural log. So this first expression is the numerator, the natural log of x minus 1 plus 3 times the natural log of x plus 5. And remember, the natural log of a quotient is equal to the difference of the logs. Again, using my rules for exponents, that 2 drops to the front. So this expression is simply using natural logs. It is actually not doing any calculus just yet. We're just using the properties of natural logs. The natural log of the product gives us the sum of the logs. The natural log of the quotient gives us the difference of the logs, and then our exponents drop to the front. All right, now let's do the second step. The second step says differentiate with respect to x. So let's move across every term and see what I got here. The derivative of the natural log of y with respect to x, using the chain rule, would equal 1 over the function multiplied by the derivative of the inside function, which I don't know what it is, so implicitly we're deriving this as dy dx. The derivative of this is 1 over the function times the derivative of the inside, which is just 1, plus the 3 is a constant multiple, gets pulled to the front. The derivative of natural log is 1 over the function multiplied by the derivative of the inside function, which again is just 1, minus the 2 is a constant, I pull it to the front. I'm taking the derivative of natural log, it would be 1 over the function multiplied by the derivative of the inside function. All right, I've taken the derivative term by term. My next step is solve for dy dx. So I'm going to cross multiply here, and I'm going to say dy dx is equal to y times what I just had there. And then my last step is this gigantic expression that I had for y. I now can substitute back into this expression for y to get my derivative in terms of just x. Now, if we were to do this using the product rule and the quotient rule and the chain rule, we might lose a couple factors here. Now, this was complicated enough just using it with logarithmic differentiation, but it could even be more complicated if we had to use the chain rule and the quotient rule and the product rule for this one. Either way, however, will give us an equivalent expression for the derivative of this function. All right, let's try number 2 on the worksheet. Let's try number 1 on the worksheet. The worksheet says, what about if we have this and I want to take the derivative of this and I want you to use logarithmic differentiation? All right, let's go through the steps. First step, take the natural log of both sides. Now let's use our rules for natural logs. Notice this is a function multiplied by a function. So we said the natural log of a product is equal to the sum of the logs. So I would take the natural log of the first thing plus the natural log of the second thing. Again, using our properties for natural log, the 4 can come to the front because it's an exponent. The 5 can come to the front because it's an exponent. So I get the natural log of 4 natural log of x. A natural log of y equals 4 natural log of x plus 5 natural log of x plus 3. All right, now I've done all of my manipulation using logs. My next step is to take the derivative of both sides term by term. Taking the derivative of both sides term by term, on this side I get 1 over y times the derivative of y with respect to x. On this side, I get the derivative of the first term, which is 4, times the derivative of this function, 1 over x, plus 5 is a constant, I pull it to the front. Derivative of natural log is 1 over the function times the derivative of the inside function, but the derivative of that inside function is just 1. There's my derivative. Now I'm going to solve for dy dx. And last step, let's put our y back in. Put that initial value that I had for y back into the expression. There's our answer using logarithmic differentiation. All right, let's do one more example from the worksheet, number 2. Y equals x to the x over 2, or remember, radical x is equal to x to the 1/2. X to the 1/2 to the x power, we multiply those together and get x to the x over 2. Now let's try our procedure. Take the natural log of both sides. Manipulate using our properties for logs. This is an exponent. It can drop in the front of the natural log. Now take the derivative of both sides of the equation. On this side, I see the product rule. On this side, I just see the natural log rule, but implicit differentiation. Taking the derivative, I get 1 over y dy dx on the left. On the right, I have to use the product rule. It would be the first function, don't do anything to it, times the derivative of the second, which is 1 over x, plus the derivative of the first function, which is 1/2, times the second, don't do anything to it. Here you can notice in this one I can simplify these x's and multiply both sides by y. So I get dy dx equals 1/2 plus 1/2 times the natural log of x. And then lastly, incorporating by putting y back in there, here is my derivative. All right, I hope that helps for having a few examples for logarithmic differentiation and the derivative of logs. Have a great week.